Okay, this is part two of the topic called goal programming. We've defined already goal programming as a specific type of linear programming formulation where you want to minimize deviations from different targets. And here we're going to review through another example the goal programming formulation. We're going to specifically talk about different types of objective functions other than just minimizing deviations from the target values. And other than reinforcing the understanding of goal programming, this will help you in understand another technique that we will hopefully cover later called multi-objective linear programming. So let's get started. So the problem statement in our example is the following. This guy Davis is the owner of a resort hotel and convention center in Myrtle Beach, South Carolina. Although his business is profitable, it is also highly seasonal. The summer months are the most profitable time of the year. To increase profits during the rest of the year, he wants to expand his convention business, but he needs to expand his conference facilities in order to do so. He hires a marketing research firm to determine the number and sizes of conference rooms that will be required by the conventions he wants to attract. The results of the study indicated that his facilities should include at least 5 small conference rooms, 10 medium rooms, and 15 large rooms, and these are the sizes in square feet for each of the rooms. So a small room is 400 square feet, a medium room is 750 square feet, and a large room is 1050 square foot. Additionally, the marketing research firm indicated that if the expansion consisted of a total of 25,000 square feet, he would have the largest convention center among his competitors, which will be desirable for advertisement purposes. And just want to point out that word, desirable. Okay, when you see stuff like that, words like that, in problems such as this one's, goal programming seems to be a good approach. Okay, because what you want to do is set up goals such that it's desirable not to deviate from them. So while discussing his expansion plans with an architect, he learned that he can expect to pay $18,000 for a small conference room, $33,000 for a medium conference room, and $45,150 for a large conference room. Okay. He would like to limit his expenditures on the convention center expansion to approximately $1 million. So this problem statement is filled with goals. Okay, he would like, for example, he wants to limit his expenditure. Notice that that's not a hard requirement. Okay, so he would like to be close to that $1 million, but the way the problem is described in here, this could certainly just work as a goal instead of a hard requirement. So, in summary, he wants to expand the convention center at his hotel in Myrtle Beach, South Carolina. He would like, and these are the goals of this problem. He would like to add 3 different types of rooms, okay, and 5 small conference rooms, 10 medium conference rooms, and 15 large conference rooms. On top of that, he would like the total expansion to be 25,000 square feet, and he would like to limit the cost to $1 million. So from here, we can see that there are 5 different goals. Okay, one goal specific to the number of small rooms, another one specific to the number of medium rooms, and another one specific to the number of large conference rooms. Okay, so those are 3 goals, and we can see that there's another goal related to the size of the expansion. He would like that to be around 25,000 square feet. That's goal number 4. And the 5th goal will be to limit the cost to $1 million. Okay? The types of conference room being considered, there's 3 conference rooms, so the decision will be mainly how many of each to build. And again, we have goals as to the number of each that we would like to have. Okay, these are the sizes which are given in the problem statement for each of the room. Small room is 400 square feet, medium room is 750, and a large room is 1050. And these are the costs per unit for each of the different rooms. Okay, so this is the problem statement and a good example to formulate this as a goal programming solution. Okay, so let's define our decision variables and goals for our problem. Based on the problem statement, we'd already figure out that what we want to do here is to understand how many of each different types of rooms to have in the expansion. Okay, so we can define our decision variables this way. So let x sub I equal to the number of I rooms to be added, where I is defined as follows. 1 is equal to small room, 2 is equal to a medium room, and 3 is equal to a large room. So we're going to have 3 decision variables in this problem. Okay, what are the goals in this problem? We sort of talked about them already. We have 5 different goals. So goal number 1 will be that the expansion should include approximately 5 small conference rooms. Okay. And goal number 2 is also related to conference rooms, but this one deals with meeting conference rooms. So the expansion should include approximately 10 meeting conference rooms. And goal number 3 is that the expansion should include approximately 15 large conference rooms. Okay. The 4th goal has to do with the expansion size. So the expansion should consist of approximately 25,000 square feet. And the 5th goal has to do with cost. It says that the expansion should cost approximately $1 million. So these are the decision variables of a problem, and these are the different set of constraints or goals for a problem. These are going to be turned into constraints. If you recall, the way you do this in goal programming is by adding deviational variables for each of the goals. Okay? And the objective in a typical goal programming problem is to minimize the deviations from each of the goals, the total number of deviations. So let's formulate linear functions for the constraints of our 5 goals. Okay, so if you remember, we have 3 decision variables in this problem: x1, x2, and x3. So x1 is equal to the number of small rooms to include, x2 is equal to the number of medium-sized rooms to include, and x3 is equal to the number of large-sized rooms to include. Okay, so for the first 3 constraints, we have to include those variables. Okay, so the expansion should include approximately 5 small conference rooms. So the way we include that goal in here as a constraint is x1, which is going to be the number of small conference rooms, plus and minus our deviations. Okay, so this d1 minus has a plus sign. This means any deviation that comes short from meeting that target goal of 5. Okay, and this negative d1 plus equals to deviation that results in going over that 5, which is our target goal. We're going to do the same approach for goals 2 and 3. So this is the function being used for representing the goal to include approximately 10 meeting conference size rooms. So it's going to be x2 plus that d2 minus d2 plus. Okay, it's equal to 10 because that's our goal. Again, this d2 minus is going to be the number of deviational units under that target value of 10. And if we happen to go over that goal value, then we're going to have some value greater than 0 for that d2 plus. Okay, so this is our function for our second goal. The third goal, pretty much following the same approach. Our goal is 15, so the number of large conference rooms, which is x of 3, plus any deviations from that 15 is going to have to be equal to 15. Okay. Now, goal number 4 has to do with that, with the expansion should consist of approximately 25,000 square feet. Okay, so these values, the 400 represent the square size per small conference room. The 750 is the square size, or the size for a medium-sized conference room. And this 1050 represents the size for a large conference room. Okay, so, and these deviational variables again are related to going either over or under that goal of $25,000. The 5th goal is related to cost. So the expansion should cost approximately $1 million, and this is given in thousands. Okay, so each unit of a small conference room costs $18,000. So that's why it's 18x1 plus 33x2. So each unit of a medium-sized room costs $33,000 plus 45.15x3 plus any deviation from our target value, which is $1 million. Okay, so I set it up in here as a 1,000. This is in thousands, so that's $1 million. So this is how we formulate the goals for this problem, and of course we want our deviational variables to be greater than or equal to 0, and eventually also our decision variables as far as x1, x2, and x3 is going to be greater than or equal to 0 as well. So let's talk in general now. General objective functions for goal programming problems. There are various ways that we can set up objective functions for a goal programming problem. Okay, I'm going to talk about 3. Okay, so the first one is, we already discussed this, where we want to, as an objective, to minimize the sum of deviations. Okay, so for each goal I, we have deviations. Okay, we can be either over or under, and we want to minimize that total sum of deviations per goal. Okay, so if we have 10 goals, we're going to have 10 different set of deviational variables, and we're going to minimize the sum of all those 10 deviations from each of the goals, from all the goals in our problem. Okay, so that's number one. The problem with this is that since deviations measure different things, it's hard to understand what does it really represent. So let's say, for example, we have in a problem only two goals. One goal that represents cost and another goal that represents number of units to be produced. So let's say that we underachieve our number of units to be produced by 10 units, and we went over our cost goal by 1,000 units. Okay, so if you follow this approach, since we only have two goals, we're going to have a total deviation of 1010. Okay, so what does it really mean? Okay, and because we went over that cost goal by 1000, but we were under or deviated from our production goal by 2. So we're talking about two different units in here. So it's really hard to make sense about that solution. So that's one type of problem. That's a key problem with the when you want to minimize sum of deviations. But that's typically used in goal programming. That's one of the commonly used objectives. But a second objective could be to minimize the sum of percentage deviations. So what we're trying to do here is get everything into a single unit. Okay, so in this case, you get everything into percentages. So that will give you a little bit more targeted information. Okay, so minimize sum of percentage deviations. What we do is for each goal, we divide the total deviation by the target value. Okay, so that T sub I represents the target value of goal I. Okay, so if our cost is to keep it at $1,000, that TI will be $1,000. Okay, so you measure the deviations from that goal. Let's say you went over 10, so your total your percentage of deviation for that particular goal is going to be 10 over $1,000. And you do the same for the rest of the goals. So it'll give you more targeted or more detailed information, because now you're getting everything in terms of one specific unit. Okay, in this case is percentage deviation. Okay, but suppose that in our example before, the first goal is underachieved by one small room, and the fifth goal is overachieved by $200,000. So if you remember, goal number one had to do with the number of small rooms to be included in the expansion, and the fifth goal had to do with cost. Okay, so I think it was $1 million, the goal for that. So that means that your solution, instead of 5 small rooms that you had before, now you have 4 small rooms. So you deviated by 1. Okay, and the same thing with the goal. You overachieve it. Instead of $1 million, you spend $1,200,000. So what does this mean? Well, if we talk in terms of percentage, because what we want to do is minimize the sum of percentage deviations, we underachieve goal number 1 by 20%. Okay, so our deviation is 1 over 5, which is the total target value. That's 20%. For goal number 5, we deviated from that also 20%. So it's $200,000 of our target value, which was $1 million. That's 20%. And so this implies that being $200,000 over budget is just as undesirable as having one too few small rooms. And I know a lot of people, a lot of decision makers will probably have issues with this. Okay, but in terms of percentage, deviation is the same. Okay, so is this really the case that these being $200,000 over budget is the same as having one too few small rooms? Okay, it can only be answered by the decision maker, but logically, you can see that a lot of decision makers would have issues with this. Okay, so that's one drawback of using this as an objective function. Minimize the sum of percentage deviations. The third objective would be, well, in previous objectives, number 1 and number 2, number 1 is minimize the total sum of deviations, and number 2 is minimize the sum of percentage deviations. We can actually include weights to each of these two scenarios. Okay, we can include weights and use them to allow the decision maker to indicate two things: desirable versus undesirable deviations, and the relative importance of various goals. Okay, so if the cost goal is much more important than number of small rooms, you obviously will increase the weight value for that for that cost goal. Okay, and what that's going to do is just gonna it's gonna direct the simplex algorithm, which is what's actually solving these linear programming formulations, to prioritize that cost goal and try to find a solution that meets that cost goal as much as possible. Okay, so it just makes sense. So for objective number 1, we can minimize the weighted sum of deviations using this formula, and all we're doing is just adding a weight parameter to each of the deviations. Okay, so if that deviation di negative is much more important than going under and having some value here in the di plus, then you'll increase the weight of that di minus deviation. Okay, and again, we just want to minimize the weighted sum of deviations in here. Okay. For objective number 2, we can minimize the weighted sum of percentage deviations. Remember, for the weighted sum of percentage deviations, all we did was divide everything, divide all the deviations by the target value for each goal. Okay, so the difference in here is that we are adding weights now. Okay, so it gives you flexibility to add relative importance of various goals and to determine which ones are the desirable and undesirable deviations as well. Okay, so this is objective number 3. Okay, it's a combination actually of the first 2 objectives. So going back to our problem, let's define the problem's objective function. Okay, but first we have to consider a few assumptions. So there's 3 assumptions here. So number 1 is it is undesirable to underachieve any of the first 3 room goals. Number 2, it's saying that it is undesirable to overachieve or underachieve the 25,000 square feet expansion goal. And number 3, it is undesirable to overachieve the $1 million total cost goal. Okay, so what is this saying? Well, saying that the decision maker is indifferent about overachieving the first 3 goal rooms. The decision maker would not like to deviate from the target of adding the 25,000 square feet, and the decision maker is pretty much indifferent about underachieving the $1 million cost goal. So as a fourth assumption, assume that the goal is to minimize the weighted percentage deviation. Okay, so if you remember, that was the objective function number 3. Okay, so one part of objective function number 3. So if we assume that the objective function becomes this linear function, and what we want to do is minimize weighted percentage of deviations. So we have weights for each deviations, and we have we get them into percentage by dividing by the target of each of the goals. Okay, and we define this objective function considering all these different assumptions. Okay, so it is undesirable to underachieve any of the first 3 goal rooms. So that's why we see this d sub 1, d sub 2, and d sub 3 negative parameters. Okay, it is undesirable to overachieve or underachieve the 25,000 square feet expansion goal. This is goal number 4. So because it is equally undesirable to overachieve or underachieve, we're going to have, for goal number 4, we're going to have the D4 negative parameter and the D4 positive parameter as well. Okay, for goal number 5, we're only going to have the D5 plus parameter included in our objective function because it specified that it is undesirable to overachieve the $1 million total cost. So it's okay, or it's desirable to be under that total cost parameter. Okay. A common question from students when you see this objective function this way is, how do we set up these values for these weights? Okay, and initially there's not really a specified rule that says you have to do this, you have to set it this way. It's really specific to the decision maker, but one thing that you can do is initially just set every weight equal to 1. Okay, and what this is saying is that each undesirable deviation has equal importance. Okay, so this can be our starting point to do our analysis. If you know this is not the case and you know specifically the relative importance of each of the different deviations from the goals, then you can go ahead and set them up relative to each other. Okay, so if you know, for example, that the deviation to goal number 2 is twice as important as that of number 1, then you can set that deviation that way for the deviation of goal number 1 to 1 and that one to 2, but then it starts becoming an issue. Okay, but as an initial point, we can say let's assume that each weight is equally important and set each individual weight equal to 1. Okay, that way we will consider it in our formulation, in our solution approach, but we just start saying that they have the same value. Okay, every single goal is equally important. Okay. So this is the final LP model formulation for goal programming example. There was only one mistake in here, and I corrected it in there. This value should be 750 x2 instead of x3. And this one represents the square footage, which is goal number 4 in our problem. But we have our objective function, which is a minimization problem, and we have our different constraints representing each of the 5 goals. We have 3 goals representing that are related to the number of different types of rooms. We have a square footage constraint or goal, and we have a cost goal. Okay, all of our deviational variables have to be greater than or equal to 0. All of our decision variables representing the number of rooms has to be greater than or equal to 0. And in this case, there's an extra constraint saying that each of the decision variables representing the x, 1, 2, and 3 must be integer values. Okay, so you cannot have fractions of those parameters. So, for example, in the number of small rooms, it has to be the solution for that. The value for the decision variable must be an integer. The same for the medium rooms and for the large rooms. Okay, so this is a complete formulation for this problem. This is an Excel solver solution for this problem. So this is a snapshot of the way that I solved this in Excel. Okay, so this is pretty much a specification of the problem in Excel. And I added here key cell formulas. Okay, so that you can actually follow this much better and you can replicate this in Excel yourselves. Okay, so we have, again, our changing cells. These are the values for our decision variables. So we have here the variables from this problem. These are decision variables, and over here we have all the deviational variables, and this is how we specify a goal programming solution. We have coefficients, we have our objective function value, we have to calculate weights. We'll go over this in a few seconds, and we have our five constraints. Okay, these are the left-hand side values of our constraints. These are the right-hand side values of the constraints, which pretty much represent target values for each of our goals. Okay, so for example, the key cell formula here to specify the objective function. Okay, so this is cell Q4. Okay, so this is going to be the sum of products of cells C4O4. So we see C4, these are changing cells, all of our changing cells in here times the coefficients. Okay, so what I'm doing here pretty much is specifying that linear objective function. Okay, notice that the variables in here that have a 0 coefficient, of course, are not going to be part of the objective function. Okay, so those variables that have in this function that should have a coefficient greater than 0 are the ones that are going to be included in here. Okay, so these are coefficients, and I'll tell you in a second how these coefficients get calculated. Okay, but these are the different variables included: D1 minus, D2 minus, D3 minus, D4 minus, 1 minus, 2 minus, 3 minus, 4 minus, and then D4 plus and D5 plus. Okay, D4 plus and D5 plus. I highlight that in yellow to make it easier to follow. Okay, so that's how you specify the objective function in Excel for this problem. It's the sum of product of C4O4 and C5O5. Now, the objective function coefficients, that's cell F5. Okay, and this is going to be repeated again for all of the different cells that are highlighted in here. Basically, what we're doing here in this case is going to be, and all I'm doing is following this. So there's going to be the weight that we specify for that deviation of goal 1 over 5, which is the target value. Okay, so notice that we started initially set every single weight equal to 1. Okay, so you see 1 for the deviation from goal 1. You see another weight of 1 for the deviation in goal 2. You see another 1 for the deviation in goal 3, and another 1 for the deviation in goal 4. And again, you have deviational variables here or the weights for these deviation variables equal to 1 here because they're included in the objective function. So d4 plus and d5 plus, which are included in the objective function, are also going to have weights of 1. Okay, because we just started this way. We say we're going to initiate a solution approach here by setting every goal, every weight equal to 1. Okay, so all we're doing here in this cell F5 is just dividing our goal, which in this case is going to be F8, over S11, which is going to be the target value for goal number 1. Okay, so that's going to give us a coefficient value of 0.2. Okay, so you repeat the same approach for all of the different goals. So for D2 is going to be 1 over 10. For D3 is going to be 1 over 15. And for D4 is going to be 1 over 25,000. Notice it's going to be the same coefficient for the D4 minus and the D4 plus. And for the D5, deviation 5 is going to be 1 over $1 million. Okay? So that's how we calculate the coefficient rho in here. Lastly, for the constrained cells, I'm going to give you an example of that Q11. So the constrained cells are this area in here. So this is the left-hand side value of our constraints. Okay, and then including deviational variables and everything, they have to be equal to the right-hand side values. These are the target values for each of our goals. Okay, so that cell Q11, it's set up as a sum of products. Again, this is a linear function, so we're including here our decision variables. So these are going to be C404. These are our changing cells. So we're going to multiply that. We're going to get that. And we're going to multiply times each of the rows of each of the constraints. Okay, so what this is saying is, for example, for this parameter, is that we're going to multiply the value for the changing cell for x1 is going to be included. So it's going to be x1 plus, the only other one here is d1 negative. So it's going to be x1 plus d1 negative minus d1 positive equals to 5. And if you recall, that's exactly the goal constraint for goal number 1. Okay? Everything else is pretty much the same. So you repeat the same approach for cell Q12, 13, and 14, and 15. Okay? This is the Excel solver formulation. So this is a snapshot of the solver formulation. Okay, so we have, this is a minimization problem again, so we specify here, and you can go back to the previous slide to get more the information related to Excel columns and rows, but the objective here is to minimize that objective function value that we set in the previous slide. So it's a minimization of that value, and what we're going to do is minimize weighted percentage deviations as we specify. Here we specify the change in cells. It's going to be C4 through 04, all those parameters, and we have our constraints. These Q11 and Q15 will represent the left-hand side values of each of the goals, and the right-hand side value, the S11 through S15, are going to represent the goals. Okay? Now there's a new one in here. Well, before we get to that, make sure that this is how you specify non-negativity constraints for each of our decision variables and the deviational variables. And we have to make sure that we select the simplex LP algorithm. Okay. Now, in the formulation, we specified that we would like for every value of our decision variables, x1, x2, and x3, be integer value variables. Okay, in Excel, in Solver, it's pretty easy. Okay, so you're going to add an extra constraint, okay, and you're going to say the values, the changing cells for x1, x2, and x3, which in this case are C4, D4, and E4, they have to be equal. So when you hit that drop-down menu in there, you're going to see a value that's going to say integer, okay, int. So when you select that, Excel automatically fills this for you. Okay, so when you select that int, it's going to set this to an equality, equal, and it's just going to type that for you, integer. Okay, when you hit OK, you're going to see this constraint in here, and that's how you specify an integer linear programming solution in Excel, in Solver. Okay, so you need to make sure that you add that as a constraint in Excel. So it seems that we have everything in place here to solve our solution. All you have to do now, there's going to be a button down here, you just press solve, and it's going to give you the solution for this problem. The solution for this problem will provide different values for decision variables, of course, x1, x2, and x3, and it's going to provide values for any deviation in here. Okay, these are basically not decision variables because you calculate this as a function of your constraints and the values for this x1, x2, and x3, which are the decision variables in this problem. Okay, notice that it gave you here, since what we want to do is minimize weighted percentage of deviation, what it gave you here provided is the weighted percentage deviation, the minimum weighted percentage deviation, which turns out to be 11%. Okay? From this solution, we can see that we are not deviating from any of the first three goals because there's the deviation variables 1, 2, and 3 are 0. Okay, and so when you're looking at this solution, you are mainly not really focusing on this value of the objective function value. You're focusing on the results, on the values for your decision variables. Okay, so what is it that the solution is telling me? It's telling me right now that I have to build, I can get away with 5 small rooms, 10 medium rooms, and 15 large rooms, and I'm not deviating from my goals, so that's okay. With respect to goal number 4, I am deviating from that goal by 250 square feet. Okay, so it deviates from goal number 4 by 250 square feet, and it deviates from the cost goal by 97,250. So that seems to be pretty significant. Okay, so given the relatively large deviation of goal 5, what we could do is change weights. Okay, so we can increase the weight value for this goal and rerun the model. Okay, so this is pretty much done if you're not, as a decision maker, if you're not really happy about this. Okay, so and it seems to be a relatively large deviation from this goal. So I'm almost $100,000 over budget. So what you can do is increase the weight for that goal, and the weight is specified here. So there's not a specific rule as to how much to increase, but you can say that you're going to increase your goals by a magnitude of 10, for example. Okay, so if you set this goal here to 10, you can rerun your model and see what the solution is. So the algorithm, what's going to try now to do is, since you increase your priority level and that goal number 5 is going to try to find a solution that meets that goal as much as possible. Okay, and then go ahead and just try to meet the other goals as much as it can. Okay, so that's one thing you can do. Okay, so let's try that. Let's increase the weight for goal number 5 from 1 to 10 and rerun the model, and we'll see what happens. Okay, so increase our weight for goal number 5 to 10, and we rerun our model. We can see now that the minimum weighted percentage deviation is much higher. Okay, it's 28, but really don't care about that right now. What we care about is looking at our values for the deviations. Okay, so it gave me x1 is equal to 5, so 5 small rooms, 10 small medium rooms, and 13 large rooms. Okay, so we can see that there's a deviation in here because our goal was to have 15 large rooms. Okay, so there's going to be a d sub 3 negative. That means that we came short 2 units of meeting that third goal, the large room goal. We can see that we deviated from goal number 4 by 1850, and an interesting factor in here is that we went over budget, but not quite as high. Okay, if you remember the previous solution, we went over budget by almost $100,000. In here, we reduced the overachievement of this goal to close to $7,000, so that's significant. However, this came at a price. We have to give 2 large conference rooms in order to do that. So that's why we see that d sub 3 minus value equals to 2. And so if this is okay, then we can go ahead with this solution. If this is unacceptable for the decision maker, then we can keep doing this process. We can increase now the penalty of D3, and if we want to just keep the same order of magnitude, we can just increase that goal, that weight, from 1 to 10. So we can set this to 10 as well and rerun the model and see if we're happy with the solution. And we can sort of like keep doing this iterative approach until we're satisfied with the results. Okay, so it's sort of like, it becomes a trial and error type of thing. Okay, but it gives you different ways to control the importance level that you give to each of these deviations to your goals. So in summary, this is a summary of the steps that you can go through to formulate goal programming solutions. Okay, so number one, identify the decision variables in the problem, of course. Number two, identify any hard constraints in the problem and formulate them in the usual way, just a usual linear programming model, no deviational variables. Number three, state the goals of the problem along with the target value. Number four, create constraints using the decision variables that would achieve the goals exactly. And number five is to actually transform the constraints into goal constraints by including deviational variables. Okay, so it's sort of following like a logical process. Okay, after you establish those deviational variables, you want to add weights to these deviational variables, and that's actually goal number 7. You want to determine which of the deviational variables represent undesirable deviations from the goals. So whether it's undesirable to overachieve or underachieve a goal. Okay? Formulate an objective that penalizes those undesirable variables. Identify appropriate weights for the objectives, solve the problem, and follow an iterative approach. So inspect the solution, and if this solution is unacceptable, then go back to step number 8, where you change weights, which represent levels of importance. You rerun the model until you find a solution that is acceptable to you or the decision maker. Okay, so this sort of like gives you a step-by-step approach of solving goal programming problems. And we went over different objective functions that you can use to specify your goal programming solutions.